Good morning. Good morning to all of you once again. Today in this session we'll be discussing alpha decay. Although we have already started alpha decay on the last class, today we'll be continuing our discussion on alpha decay and we'll try to complete for today in this session. Before I start, let me know if everything is all right. Okay. So whenever a nucleus nuclides undergoes alpha decay, its Z value decreases by 2 unit and the mass number means A value decreases by 4 unit. Okay. Good morning, Ajay. Suddenly, I am feeling like a cold morning. Winter is coming. Okay, so let us start with the velocity of alpha particle. So you must have seen the picture where a radioactive substance was emitting different kinds of particle. It was emitting, let's say, alpha, beta and gamma, and depending on their nature, the particles were getting attracted. Now, so if you give a positive potential, then beta particles big because they are basically negatively charged particle, so they will get attracted towards the positive plate, and alpha particle being positive, it will get attracted towards the negative plates. So you also have seen this picture that whenever a charged particle enters into a field, it will create circular paths if it is if it is entering the magnetic field perpendicular to the magnetic. If you consider an inward or upward magnetic field and a charged particle enters, it will make a circular trajectory. So let V be the velocity of the alpha particles, M be its mass, Q is the charge, R is the radius, and B is the magnetic field. Then we can have this relation. You have already seen V is equals to BQR by M. This you can get by equating the magnetic force and centrifugal force. Now, good morning, Harry. Let's talk about range of alpha particles. What is there in this range? So let's say if you have a material, a medium, let's say, it may contain some gas or something else. So it's a medium containing something. Now, into this medium, if you send the alpha particles, it will not continue to pass through the medium without attenuation. It will attenuate, right? With time, with distance, it will get attenuated like this. So distance through which an alpha particle travels in a specified material before stopping to ionize it is called the range of alpha particles in that material. So while going through the material, let's say the alpha particle will ionize the material. Okay, let's say if you have an atom and it releases electron, it will become A positive, right? So this is the meaning of ionization. So this is A plus ion and this is the atom. So whenever alpha particle travels through a medium, it will ionize the material inside it, and the distance up to which it will do this thing, ionization process, that thing is called range of alpha particles. Now it is quite obvious that depending on the material, the alpha particle range will be different. So the range is sharply defined as ionization path length. Ionization path length. And on which factors the range will depend? Obviously, if the alpha particle energy is more, it will continue to ionize for a larger distance. The initial energy of the alpha particle is deciding the range. Secondly, the ionization potential of the gas. How easy or how difficult for the alpha particle to ionize the constituent elements in this medium, that will also depend on the range. If it takes more energy to ionize particular let's say gas, then obviously it will not be able to go much distance. But if the ionization potential is less, it can go up to a further distance. Third point is the chance of collision between alpha particles. So what does this point say? If let's say there are more number of atoms, so alpha particle we have to collide with more number of atoms, and as a result it will lose its energy more quickly. If there are less number of let's say atoms, so it will have to collide with less number of atoms, and less collision means the energy loss by alpha particle due to collision will be less, and the range will automatically increase. Fourth one, on the nature and temperature and pressure of the gas. Will be nature of on the nature of the temperature and pressure of the gas. With the increase of pressure, range decreases. If you increase the pressure, range decreases. Pressure you increase, your range will decrease. It increases if the temperature of the gas increases. If you increase the temperature, the range will increase. So this so I hope this is a quite understandable theoretical thing. Now instead of considering this as a medium, in a medium, if you consider like what will happen, what is the case for the normal air in which we are living, if the alpha particle is sent through air, how the range gets affected. You don't need to write this, just try to understand this. I'll share this PDF, don't worry. Now instead of let's say I'm just for the generalization purpose I'm showing the air medium. Okay, so alpha particle is coming, I'm just showing it in the form of a wave. Now it is not vacuum, it is air, so it will attenuate, but it will attenuate in less amount. Okay? So how the range and the alpha particle velocity is connected? See, the range R, this one you can write in standard air is proportional to VQ, proportional to velocity. Third power of velocity, that is range. This is not radius, okay, this is range. Now let's say this is the proportionality constant is A, so you get a relation R is equals to AB. This relation is known as Geiger law. And this is valid for only limited velocity range, valid for limited velocity. Good morning, Murli. Now you see, R is proportional to VQ, and energy of the alpha particle. This is the velocity v with which the alpha particles are moving. So this is, I have just plotted the intensity, but you can imagine alpha particle is basically corpuscular, right? So you can imagine it like particles, but intensity, to represent intensity, we are representing in the form of wave. Intensity is slowly decreasing. Now energy of the alpha particle, the energy of the alpha particle, if you write, what is the energy? E, if we write E is equals to half m v square. So from these two relations, so R proportional to V cube and E proportional to V square, from this can we find a relationship between the range and the energy? Range energy relationship is, what will you get? Look, R is proportional to V cube. So R will be proportional to, here, from here you can see V is proportional to e to the power half, right? So R is proportional to V cube and V is proportional to e to the power half, so cube. Can we say? And that makes R is equals to, let's take some other proportionality constant, that is B. So B e to the power 3 by 2. So this is the relation between the range and the energy of the alpha particle. So simple. Now there is a term called specific ionization of alpha particle. I forget always my coffee. Note it down. Look, specific ionization of alpha particle. So if you imagine, let's say the alpha particle is going through some medium. So let's say some medium, there may be a gas or something. Now let's say alpha particle is going through it. What will happen? It will continue to ionize the gases or those things, atoms inside it. So as I told you, it will create positive ion and negative ion. So these are ion pairs. Okay, this is one ion pair. So whenever a positive ion is created, because of the electron, there will be a negative ion. So this is called ion pair. So it will be some positive, negative, positive, negative. So these ion pairs will be created. So specific ionization is defined in that way. So the number of ion pairs formed per unit length. Number of ion pairs formed per unit length by an alpha particle is called specific ionization. After traveling unit distance, the number of ion pairs it formed, that gives you the specific ionization, let's say I. Specific ionization I. Now if I calculate, look, as the alpha particle is moving into the medium, it is continuing to lose its energy, right? As it covering the distance inside the medium, the energy is keep on decreasing. Now energy loss per unit length, if you calculate, energy loss per unit distance, what will be the energy loss per unit distance? You see, E, we have found out that it is proportional to R is equals to B to the power 3 by 2. So E will be proportional to R to the power 2 by 3. Can you write it from this relation? So energy loss per unit distance means it is dE upon dr. It is proportional to R to the power 2/3 minus 1, so minus 1/3. Now R is proportional to V cube. This is proportional to V to the power minus 1 by V. So when the alpha particle will be having with greater velocity, its energy loss will be less or more? Will be less. And in contrast, as the alpha particle slows down, as the alpha particle slows down, means V is decreasing. V is decreasing because this is energy loss per unit distance, d by dr is inversely proportional to V. If V decreases, d by dr will be increasing, dE by dr increases, leading to higher specific ionization. Now, if you have done practical in your MSc, I had nuclear physics special paper in my MSc, so that is why I have done these experiments regarding this range. So what happens if you talk about experimentally? We have some source of alpha particles, some radioactive nucleus. Okay, so some source we had at that time. It came in the form of a coin, okay? Like a plastic type thing. Inside there may be some little amount of radioactive sample. So those are not harmful, so much harmful. Obviously, if it were harmful, they would have not allowed it at our university, but we did some experiment. So we did the experiment with scintillation detector. So some source is there. This source, let's say S, this source will emit alpha particle, and at some distance a scintillation detector is placed. Scintillation means, you know, like whenever some excitation, maybe light, falls on it, it glows. That is the scintillation. We had a scintillation detector like this. In scintillation detector, we have some photomultiplier tube. So I'm just writing in short photomultiplier. So whenever we will discuss the radioactive detector, we'll talk about this in more detail. For the timing, you know, this is your scintillating material phosphor, ZNS. So this is the detector T, let's say. Now, by varying the distance between the source and the detector, a graph is plotted. Okay, so for a particular distance, the intensity of the alpha particle is noted down, is recorded. Now, by varying the distance between the source and the detector, we plot the intensity versus distance curve. So it somewhat looks like this. If you plot intensity versus distance, so you see, when it will get slowed down, then the energy loss will be more. So initially there is not much energy loss. Energy loss directly reflects the reduction in intensity, right? So it will not fall so sharply. So there will be an extrapolated range. Doesn't fall sharply, it falls like this. So we have A, and here we have B, the mean range. The this is the mean range. So this alpha particle range determination is a statistical process. So the range will be more or less an average number, okay, but there is some shift around the mean range. Mean range is not a fixed value. You get a shift in the mean range. That is called staggering. We'll talk about it today only. So this is your extrapolated range. Extrapolated range. Let me tell you what is exactly we are doing. So the distance between the source S and the scintillating detector, scintillation detector T, is gradually increased and plot of intensity versus distance is made. And this is the variation of the alpha particles intensity with distance. Now, when the intensity reduces almost half of its initial intensity, you can see this gives you the mean range. What is mean range? Mean range. The distance from the source at which the intensity is half of the initial intensity. It's called the mean range. R. So what does it mean? Intensity is reduced to half means 50% of the alpha particle have range less than R and 50% of the particle have range more than R. We can conclude in that way, implying that 50% of the alpha particles have range more than R and 50%, the remaining 50% have ranges less than R. Now, if you send alpha particle with same energies, so each time will the range will be same initial intensity alpha particle you are sending, will you get same range every time? The answer is no. You will not get same range every time because the collisions it undergoes inside the material. That is a statistical process. So although there will be an average range, there will be a little bit shift around the average value. It is not exactly the same constant value you will every time you will get. Even if you are keeping everything same, you are keeping the initial energy same, the medium same, then also you will get a differing range. Slightly it will get deviated. That is called straggling, STRAGGLING, straggling of the range. Okay, so let's talk about that straggling of the range. The alpha particles of the same energy, same initial energy, let's say, have more or less the same range in a given substance. However, a small spread in the value of ranges about the mean value is observed. This phenomena is known as the struggling of alpha particles. The struggling of the range, not alpha. Extrapolate range from where it starts in the graph. You see, after this mean range, it will decrease in this flat way. This is the extrapolated range. You can consider like after the mean range, the extrapolated range is plotted. Okay, Murli. Now you see, when the alpha particle is going through the medium, it is losing its energy. So what is basically the medium doing? The medium is basically stopping the alpha particle. If there is no medium, alpha particle will go without losing its energy, without losing its intensity. So what does the medium does? It basically stops the alpha particle. So for a particular medium, we can define the stopping power. Okay, stopping power of a material. So it is defined from the energy loss. Energy loss, we have got dE by dr. So dE, that thing is what? Negative. Dr, that thing is positive. So the whole thing is negative. So when we define the stopping power, we just add a minus sign. We multiply a minus sign with the energy loss, and we get the stopping power of the material. So let's talk about the stopping power. Today's class is a little bit theoretical. The mathematical portion is also there. The stopping power of a material describes how much energy is lost per unit length. How much energy is lost per unit length. So how will you express stopping power? Stopping power is just the negative of the energy loss minus dE by dx. dE by dx is the energy loss per unit length. So energy loss per unit. Okay. So this is stopping power. Now there is something called mass stopping power. So mass stopping power, when it is talking about the mass stopping power, it is just divided by the mass density. Rho is what? Rho is the density of the material. Mass density. Now there is something called atomic stopping power. What will be atomic stopping power? So if you divide mass stopping power by the number of atoms per unit volume in the material, we get atomic stopping power. If you divide the mass stopping power by the number of atoms per unit volume in the material, we get the atomic stopping power. So these are some terms which you should keep in mind. So we have got Geiger law. Geiger law was this. Where is Geiger law? Yes, R is proportional to VQ. Now there is something called Geiger-Newton law. Is it done? Geiger-Newton law is basically a simple thing. Ln lambda is equals to A plus B ln R. What is lambda here? Lambda is the decay constant of the radioactive element. This is known as Geiger-Newton law. Lambda is the decay constant of the radioactive element. What is R? R is the range of the emitter alpha particles. And what is A and B? A and B are the constants. That depend on the specific isotopes. So this Geiger-Nuttall law basically establishes a relationship between the decay constant and the range. So it shows a linear relationship between the logarithm of decay constant and the logarithm of range of the alpha particle. So this will help us to understand the behavior of the decay behavior of the alpha nuclei, alpha emitting nuclei. Now if we plot it, does it create ion pairs until the energy loss to the minimum energy of alpha particles? Yes. It is not able to ionize the alpha particle. It is not able to ionize the medium particle, means it doesn't have sufficient energy. So it will get stopped, right? The ionization energy is very less, if you see, but the energy of the alpha particle is in the order of sometimes mega electron volt. You consider that ionization potential you can get in electron volt order, but the energy of the alpha particle you will get it in the mega electron volt order. See how large the energy of the alpha particle is. So whatever atoms will come across to the path of the alpha particle, they will get ionized. So this will give you straight lines like this. So after fitting this curve, you can get the value of A and B, and from that you can find a relationship between the decay constant and the range. The first one is 1, let's say 2, this is for uranium series, this is for thorium series, this is for actinium series. So we talked about this series, right? So it starts with the parent nuclei and it goes through disintegration and it gives successive daughter nuclei, and ultimately it ends with a stable product. Now ln lambda is equals to A plus B ln R. So we can also represent it in an alternative form. If you see, R is proportional to, we have already calculated, it is proportional to e to the power 3 by 2. Now if I put this value of R here, e to the power 3 by 2, some other constant will come, but it will become ln E. So the constants are changing. Ln lambda is equal to C plus D times ln E. So this is another form of Geiger-Nuttall law involving the decay constant and the energy. Is it done? Let us now talk about a very important theory, Gamow theory of alpha decay. So Gamow's theory of alpha decay gives you the explanation how alpha particles gets emitted from the nucleus. If you have seen, the alpha particle energy is about 4 to 9 MeV. Remember this thing. Alpha particles energy we generally see which are getting emitted from the nucleus. The energy is around 4 to 9 MeV. But inside the nucleus, the barrier potential is of the order of 25 MeV. So how does the alpha particle is coming out of the nucleus? That is the question. That was the problem the scientist faced, and Gamow ultimately gave the proper description of this thing. How is it possible? Classically it is not possible, right? If you have less energy, if let's say you are behind a big wall, can you jump over it? You don't have that much energy to jump over the wall. So classically you cannot be on the other side of the wall, but quantum mechanically there is a finite possibility that you can be found on the other side of the wall. So this concept is called tunneling. Okay. So although the alpha particle's energy is very low, 4 to 9 MeV, as compared to the Coulomb barrier, as compared to the barrier potential of 25 MeV, it uses the process of quantum mechanical tunneling to come out of the nucleus. Okay. So the basic idea is, inside the nucleus, the alpha particle just bypass, you can say bypass the huge potential barrier using the process of quantum mechanical tunneling, and once it is out of the nucleus, the Coulomb repulsion helps it to come out of that atom. Okay, so let's talk about this Gamow's theory. I hope you got a simple overview of the thing which you are going to do next. Gamow's theory of alpha decay. In 1928, this was the year, George Gamow proposed a successful theory of alpha decay, according to which the alpha particles move freely inside the nucleus. The alpha particles move freely inside the nucleus, and it is emitted after tunneling through the potential barrier. Simple thing. Now there were some basic assumptions of Gamow's theory of alpha decay. The first assumption was an alpha particle before emission exists as an entity within a heavy nucleus. Okay? Exists as an entity. Number two, an alpha particle moves with constant velocity within the nucleus and bounces back and forth from the barrier wall. So it is behaving like this. Alpha particle is there, it is moving back and forth, back and forth. So these are like the barrier walls, you can say. Due to quantum mechanical tunneling effect, this is the most important. Quantum mechanical tunneling effect, there is a small probability of leakage of the alpha particle through the barrier each time it collides with the surface of the nucleus. Okay, we'll later on see how many times it hits the wall. Once outside the potential barrier, the short range nuclear forces vanish. You know, nuclear force acts in a very short range, but the Coulomb force, it extends up to infinity ideally, right? So once it is out of the potential barrier, it will escape from the nucleus due to the Coulomb repulsive force between the alpha particle and the daughter nucleus. Nucleus is basically positively charged because of the number of protons, and alpha particle is positive in itself. So the Coulomb repulsion helps it to move away from the nucleus. So these are some basic things. Main thing is the quantum mechanical tunneling. So if we try to understand this thing in the form of a figure, let's say energy versus R, we are plotting, and you will see how things go. Along the y-axis we are plotting, let's say, energy, and along x-axis we have the radial distance r. Now this r naught is, let's say, the nuclear radius, capital R naught we are denoting, or you can also denote it by capital R is the radius. Don't get confused with the range, radius. So this is your zero line. Now the potential well is extend up to negative. So this is inside the nucleus. You can see this is in the rectangular form, and as you are out of the nucleus, you know what behavior you will get. You will get a behavior of Coulomb potential, right? Like this. So you will get it like 1 by r. In this form you will get. Now this is, let's say, minus V0. Now the maximum, you can say, here. The alpha particle is here, it is bouncing back and forth between the walls. So because of the limitation of the alpha particle's energy, because it is 4 to 9 MeV, it cannot escape. Alpha particle cannot escape classically. And here you can say alpha particle cannot enter also classically. Alpha particle cannot enter classically. This is the total range of this range corresponding to the kinetic energy of the alpha particle. This gives you this much of energy, gives you the kinetic energy of alpha particle. So classically it is not possible to have any alpha particle decay. Why it starts from negative potential? This is an attractive potential. Now we have talked about the nuclear potential, you have seen it is negative. The potential well, right? Potential well which is binding the nucleons, it is negative now. If it is not well, the particle will escape. Okay, so this is the classical picture. You can say this is our classical picture. Let's name this as figure A. You see, let us write few things. The height of the potential barrier is about 25 mega electron, which is equal to the work that must be done against the repulsive electric force to bring an alpha particle from infinity to the nuclear radius, or infinity to a position closer to the nucleus. Adjacent to the nucleus, but just outside the range of attractive force. So here the main important thing is this 25 MeV. Now, on the other hand, alpha particles have energies in the range 4 to 9 MeV. This is another important thing. So depending on the particular nuclei involved. Therefore, classically, an alpha particle cannot enter और एस्केप, ना बाहर जा सकता है ना अंदर आ सकता है. An alpha particle cannot enter or escape the nucleus. Whose radius is, let's say, r. Now, as for this GAMO, he shows that there is a finite probability. So, if you consider quantum mechanically, how this picture changes. What does it show? This peak is the Coulomb barrier, right? So in this picture, two types of forces are being shown. One, this up to 0 to r, this portion up to 0 to r represented by the rectangular potential. You can see this is your strong nuclear force, which is binding the nucleons together inside the nucleus. Now, once you come out of the nucleus, you have your Coulomb forces, Coulomb repulsive forces. So you can imagine it from this side. Okay, so you are moving from this side to this side. It means what? You are getting closer to the nucleus. So as you get closer to the nucleus, the protons inside the nucleus will repel. If you are taking an alpha particle, a positive thing, the positive thing will get repelled by this proton inside the nucleus. So as you goes closer to the nucleus, you see the Coulomb barrier is increasing, and it is becoming maximum. The maximum height of the Coulomb barrier you get at when you are just outside the nucleus. So this position actually shows just outside the nucleus. Here it is maximum. As you go away from the nucleus, the Coulomb repulsion decreases. I think this picture is clear. Now this is the classical picture. Now quantum mechanically what happens, let us talk about in figure B. Is the slide done? Look, quantum mechanically we can apply the wave particle duality theorem. Any particle behaves as wave, a wave behaves as particle. Alpha particle is a quantum mechanical entity. So we can imagine its wave behavior. So let's talk about this figure B. So we will draw a similar kind of picture here. So this is your zero line, and let's say this is, we are plotting the potential V of R versus R. This is your R, this is minus V naught. And let us draw a line. This line gives you the idea of the kinetic energy of the alpha particle, and it falls off 1 by R like this. The Coulomb barrier. So it remains under the influence of the you can say the Coulomb barrier up to this distance. So what happens quantum mechanically? If I consider a wave-like behavior, what exactly happens? Here inside the nucleus we have this wave function in this way. Now we will be talking about this tunneling later on in quantum mechanics. So it varies that it decays exponentially inside this, and it decays exponentially to this, and after crossing this it will maintain its wave behavior and it will finally comes to it. So this was the emitted alpha particle. So although classically it was not possible to cross this barrier, but quantum mechanically with the help of tunneling it is possible to come out of the nucleus. So when you will be doing in quantum mechanics, you will see this, we can write a wave function inside the nucleus and outside the nucleus. So if I write the wave function, let's say inside the nucleus where your r is less than r, so this wave function is written in this form: a e to the power I k r plus b e to the power minus I k r. This is a particle in a box problem. We'll talk about in detail while discussing quantum mechanics. But I think you must be knowing it if you have done it in your BSc. BSc also you have this. So if okay, where should it be maximum as per according to you? Obviously, where the distance is less, it is like what? Nucleus is a sum of protons. So if you are close to the nucleus, then the Coulomb barrier will be most, and as you go away from the nucleus, then the Coulomb barrier or Coulomb potential will fall off. And the maximum is the Coulomb barrier. Where the barrier is maximum, that is called a Coulomb barrier. No, there is nothing like barrier width. You can see this Coulomb potential extends up to infinity. Now this just shows here it is overcoming the influence. B doesn't have any much significance. If you are confused with it, just you can ignore. B doesn't hold any much significance. Here the R thing is important. R and the Coulomb barrier. Now in one sense, R to B, we can say barrier width, yes, because the tunneling thing is happening within this region, right? Tunneling is happening in this region. Here it is falling as exponential minus r. Here it is falling as exponential minus r. So you can see it is a barrier width in the language of quantum mechanics. And this much of energy, this is the kinetic energy of alpha. Okay, Murli. So we can, okay, let's name this the barrier width. So probability of tunneling will increase if the barrier width is less, or the kinetic energy of the alpha particle is more, then the probability of penetration will be increased. So you understood this theory, right, everybody? So not only Gamow, there were two other scientists who collaborated with Gamow. So one name is Gamow, another is Condon and Garni. These were the three scientists. They showed quantum mechanically that it is being carried out via the tunneling process. Showed quantum mechanically that there is a finite chance for an alpha particle with energy less than the barrier height, potential barrier, to leak through the barrier. This effect is called the tunnel effect. As you can see, it is proportional to e to the power minus r, so it decreases with distance. Now the probability of penetration decreases with increasing barrier width and decreasing peak alpha. Let me know if it is done, then we'll go for this thing. We'll talk about the collision frequency. How frequently the alpha particles collide. What do you think? As I told you, the alpha particle is trying to come out of the nucleus. So it is hitting the wall. Can you guess, like in 1 second, how many times it can hit? Is it 100 times in 1 second, or 1000 times, or 10,000 times, or 1 lakh times, or 1 crore time? How many times it is hitting the wall as per you? According to you, how many times the alpha particle is hitting the wall? Just make like guess on the higher end, okay, as much as you can think. Can you tell me what should be the number of times it can hit the wall? When you will get the actual number, it will blow your mind. You will feel alpha particle is so desperate to come out of the nucleus. It is hitting so many times. Any guess? Anyone you would like to make? Harry, Murli, Ajay? You can think as much higher number as possible, as big number as possible. If lakh, crore is not sufficient, you can express it in powers of 10. 1000 is 10 to the power 3. 10,000 10 to the power 4. 1 lakh. 10 lakh 10 to the power 6. Infinite. Infinite times. This is not infinite. Infinite is not a number, right? Infinite is not definite. But it should be a finite number, right? In 1 second, alpha particle is hitting the wall. It should not be infinite. 10? Only 10 times? Do you think alpha particle, if it hits 10 times, it will be able to come out of the nucleus? We're talking about nucleus. Can you imagine? You can imagine like some ball. kept in a like concreted room. So you can imagine how many times it should hit so that it will come out. Now imagine that is a very small particle and it is inside the nucleus. As I told you, imagine as big number as possible which is coming into your mind. You can use 10 powers. Not able to think. Okay, if you are not able to think, let's try to calculate and see. Look, the alpha particle moves back and forth with velocity v. So you can imagine a picture like this. Just a moment. Okay, so you imagine a situation like this. So the alpha particle is basically moving in this 2r range, na? Will go and hit. The alpha particle moves back and forth with velocity v along the radius, and will reach the barrier at r is equals to capital R, a certain time per second. We'll calculate that certain time, how many times, given by C V by 2R. This represents the frequency of heating. This represents the frequency of the alpha particle hitting the barrier or hitting the wall. Now you see the decay constant has a relation with this. Now decay constant, if you talk about, decay constant is lambda. Lambda is proportional to this frequency, collision frequency. This actually V by 2R is collision frequency times the tunneling probability. So nu is equals to V by 2R times V upon 2r is the collision frequency. T tunneling probability. Now let us try to answer that question, that how many times it should hit. So we can use this nu is equals to V by 2r formula. We can use some typical values of this V. We know the values. For typical values, the velocity V of the alpha particle, velocity we know na, velocity V of the alpha particle, how fast it moves, it is approximately 2 into 10 to the power 7 meter per second. This is the velocity, and if you take the radius, so you need V by 2r, so we need the radius value also. Radius r is about how much? 1 femtometer or less, 10 to the minus 14 meter, you can say. This is the nuclear radius. If you substitute all these value, then we get the collision frequency nu is equals to V by 2r. So V is 2 into 10 to the power 7 times 2 into 10 to the power minus 14. So this will give you the collision frequency in the unit of second inverse. So it will approximately 10 to the power 21. Okay na? 10 to the power 21. So you can imagine how big this number is. 10 to the power 21 per second. Is it understood? Murli, Ajay, Hari. Now only one thing is left that is very important for your examination. We'll do that and we'll conclude the session afterwards. Okay, look at this thing now. Alpha decay through tunneling. So what happens in alpha decay? Zxa becoming Z minus 2, Y A minus 4 and plus 2He. So if I want to calculate the barrier potential, sometimes look, this barrier potential will be different for different nuclei, you know, depending on the x whatever nuclei it is, the barrier potential V of r will be different. So nuclear radius is given by r is equals to r naught into a prime to the power 1 by 3. Here you will consider r is equals to r naught, which is this small r naught, a prime to the power 1 by 3. This thing you need to keep in mind here whenever you solve the problem. Here instead of a to the power 1 by 3 we will write a prime. This is done to take care of both the effects. You see, it was previously a, it generates a minus 4. Here a prime will have a minus 4 to the power 1 by 3 plus 4 to the power 1 by 3. So whenever you will calculate this r value, you will use this a prime. then the barrier potential will be, look, the charge, it is 1, what is the potential formula? 1 by 4 pi epsilon naught q1 q2 divided by r. This is the formula, na? In electrostatic we will read this. So here 1 by 4 pi epsilon q1, it is the, look, 2e. Charge of alpha particle is plus 2e, so 2e. Charge of this y nuclear, daughter nucleus, z minus 2e. So 2 into z minus 2e, z minus 2e into e is divided by 4 pi epsilon r. So this r, if you want to calculate, you have to use this formula, r naught a prime to the power 1 by 3, where a prime is a minus 4 to the power 1 by 3 plus 4 to the power 1 by 3, which is the Coulomb potential that alpha particle must tunnel through. Velocity of the alpha particle is root over twice e by m alpha. This is you can get it from the E equals to half mv square formula. E is the energy and m alpha is the mass of the alpha particle. Tunneling probability is given by T is equals to e to the power minus g. This is another very important formula. Formula for tunneling probability, e to the power minus g. G is a constant where g is given by this expression, a times z minus 2 e to the power minus half minus b times z minus 2 to the power half r to the power half. You don't need to remember this, okay? You just remember this T is equals to e to the power minus g formula. A, B are constant, usually derived from the fitting models to experimental data, depend on the system. This formula represents the probability of an alpha particle successfully tunneling through the potential barrier. So this is a quantitative formula. So the main formula here is this: V of r, potential barrier formula. V of r is equals to 2 into z minus 2 e square by 4 pi epsilon naught r. And sometimes this tunneling probability, you may be asked, g equals to e to the power minus g, where g is given by this. Now let me show you a question. So you understood now what you have to do in your examination. Generally this barrier potential is given. What is happening, guys? Is it done? Look at this problem. An alpha particle is emitted by 92 thorium 230 nucleus. Assuming the potential to be purely Coulombic beyond the point of separation, the height of Coulomb barrier is. So you have to find out Vc or V naught. Coulomb barrier, Vc, you can say. Now what did we represent it? V of r. Or you can also say Coulomb barrier is Vc. You know the formula of Vc. Two times z minus 2 e square by 4 pi epsilon naught r. Now determining this r is important. Look, 90 thorium 230. This is the nucleus given to you. Now if it emits alpha particle, it becomes 88. 88 is radium, I think. है ना? Oh, 88, whose atomic number is 88? Just check it with, I think, radium. 230, so 226 plus 2He. Can anyone confirm this? Is it radium or anything else? 88. So R0 is 1.30 femtometer, it is given. E square by 4 pi epsilon naught is also given. Okay. So R is R0 A prime to the power 1 by 3. R0 is given to you 1.30 femtometer, that is okay. A prime to the power 1/3 will be equals to eight radium, na? Yes. Hello. So here you have to put 226 to the power 1 by 3 plus 4 to the power 1 by. So how much you will get? 226. Where is my calculator? .09, right? 4 to the power 1 by 3. 1.58. .67 approximately. Then the Coulomb potential Vc is equals to 1 by 4 pi epsilon naught E square by R is equals to R naught A prime to the power 1 by 3. We are writing the formula directly into 2 times z minus 2. So let's put all the values. 1 by 4 pi epsilon naught E square by 4 pi epsilon naught. Okay, the whatever values are given, we'll just gather them to one place. This is E square 2 into E square by 4 pi epsilon naught. This is 1.44 MeV. Into 2 into z minus 2. Z is z minus 2 is 88, na? Divided by R naught. R naught is 1.30 femtometer. A prime to the power 1 by 3 is 7.67. So let us calculate. Acha, MEB femtometer is also there. But this minus sign is too big. I missed that for me. So whatever result you will get, Ajay, you are getting option A. Let's see if you get option A. 25.4177. Rocks. So this is matching with option A. So whenever you will be given such questions, you can proceed in this way. It takes care of both daughter nuclei and alpha particles. So 226 to the power 1 by 3, 4 to the 1 by 3. So I think this is sufficient for alpha decay. On the next day onwards, we'll start beta decay and gamma decay. Till then, bye bye. Take care. Have a great day. I hope you have got good insight from this lecture and you will find this lecture useful. Bye bye. Take care.